Today we will introduce how should we use Colab to implement facility location models. Here we have already introduced the package NumPy, plotting functions, math functions, and then we introduce a new package called CVXPY, which is also an open source solver which aims to solve all kinds of convex programming, including integer decisions. So first, we set the random seed to initiate our input. We can randomly generate several points in a 2D plane as we did for TSP and VRP. Here we set 30 due to the problem scale. And then we assume that there are 30 customers and also each customer locations are considered as a candidate facility location. So our choices for customers, which is 0 to 29. And then similarly, we have the choices of facility locations indexed by 0 to 29. And then the initialization of the points and then the distance matrix are the same as our TSP and VRP. Here we just change the notation from C cost to this D, which is the distance. So here in particular, we introduce a facility setup cost, which also is random number. Now we assume this random number is from 10 to 20. That means the facility cost varies from 10 to 20 of all possible locations. So first, let's focus on the set covering problem. Remember our set covering problem, which is minimization of fixed cost given the decision variable, which is facility setup decisions, and then the constraint, the assignment constraint. So here to implement this, first we need to generate a coverage distance. Here we assume it's to be 3. And then from the distance matrix we give D, we can calculate if Dij is smaller than this coverage distance, then we'll assume that this is covered. So Aij is 1. And otherwise Dij will be 0. So this is a Boolean matrix, which can be simply implemented by Python by 2D list. And then the interesting thing for the CVXPy package is that the optimization problem can be written in a more intuitive ways. For example, here we use the CVXPY package, which is abbreviated by CP here. So we create a variable, we just define variable here. And then the variable is a vector with n element, then the size is n. And then we tell it is a binary decision variable, that means it's Boolean. And then we can immediately write the problem, use very simple syntax. So here we assume the problem equals to a problem. And then the problem considers 2 parameters. The first parameter is the objective. And then the second parameter is the constraint. So in this way, the problem structure looks almost the same as the mathematical formula. So here we want to calculate the summation of fj, xj as an objective. This can be done by cp.sum. And then because we can sum over all j, we enumerate all possible j. So this gives us the minimization for the objective. And then the constraint, we only have one possible set of constraints. So here we just enumerate all possible customers I. And then for each customer I, we calculate the sum of Aij times xj to guarantee that this is greater or equal to 1. Because this is a series of constraints, so all these constraints are connected by a list. So here we just use one line, which can describe this one line constraint, which is very intuitive. Okay, after we create the problem, we can just use the method solve to solve the problem. And we can also print out the optimal value based on the problem dot value. So here you can see after we assume the coverage distance is 3, the optimum value for total cost is 58.6. And then from the figure, we can show that there are 5 locations built. Because the coverage is 3, we can almost draw a coverage region like this, like this, like this, this, on this. So all the points will be covered based on our constraint. The realization of set covering model in this way is pretty direct. And next is the maximum covering problem. So recall that it's a slightly different than set covering problem. In particular, the problem becomes a maximization for coverage. For each customer, we have the choices of covering it or not by z. And then our decision variable is x and z. And then our constraint is that our number of facilities opened is less than a capacity P. And then we have assignment decisions. It's the same as the previous set covering problem. So here, similarly, we have a given coverage the same as previous. And then in addition, we give the demand for customers, which is 1 for every location. You can vary the demand based on the specific problem. And then here we assume we need to guarantee that there are at most 4 facilities to be built. And then we have introduced x and z as our decision variable, which indicates x indicates the facility location decisions, and then z indicates the coverage decisions. So similarly, we can see the problem structure looks exactly the same as the formula. The same CP dot problem, and then we want to take the maximization. So here we can simplify the expression by just multiply h and z together because they are just all vectors. And then the constraint here is a little bit interesting because we have two sets of constraints. The first one is relatively simple. We just sum all over x value and then guarantee that it is small or equal to b. And then to connect the constraint together, we use a plus operations to expand the list. And then the next group of constraints, we have the same as before. We enumerate all possible j and then sum up aij and xj. And then this is for every customer. Remember previously, this is greater or equal to 1, but now it's greater or equal to the decision variable z. So after we put the problem, we just solve it again and then show the optimum solution. Now the optimum solution should be the coverage. Remember, we have 30 customers, so our coverage now is 28. That means we have 2 customers which cannot be covered. From the result, we can see that there are at most 4 facilities open. So there are 1, 2, 3, 4. And then because we have this constraint, so 2 customers have to be dropped. 1 is in here, 1 is in here. This is the optimum solution. So now let's focus on the center model. Remember, our center model is almost the same as the covering model, but with the coverage distance can be changed. So the decision is the coverage distance, and then Also, we have the facility location decisions and the customer assignment decisions together with distance. Okay, and then we need to guarantee that the constraint for all facilities is P. And then we have our distance coverage and then summation of choice. And also the assignment of customer has to be smaller or equal to the facility opening decision. So we can realize all this by the similar structure. We define problem, and then the first parameter is the objective, minimize D. And then the variable of D is defined just a normal variable with one scalar. And then we have a set of constraints. So the summation equals to P for all facility location decisions. And then the distance, choices, and then with feasibility of assignment. Every set of constraints we can use a list to represent it, and then we sum up all the lists together to create a big list which contains all the constraints. Similarly, we can just do solve, and then we can show the value, and then the coverage distance, the minimum coverage distance is 4.2, given that here we have 3 facilities. We can see the facility build 1, 2, 3, and then the green lines indicates assignment decision, which is a Yij. And we can see the customer are assigned relatively with the same size of circle. This is a feature of the center models. Now let's look at the median model. In the median model, we will consider an average or aggregated distance as our measure. So here in particular, we minimize the total travel distance, demand at each location times the travel distance times the customer assignment. And then we have our decision variable is locations and then assignment. And then our constraint. Similarly, we have our all facility locations is given by a certain number P, which is the same as the central model. In addition, we just have the feasibility and then choice model. So here to realize this, similarly we define P given 3, and then we have decision variable X and Y. So because now we have the problem, we calculate the summation in the objective, similar structure, and then we have 3 sets of constraints. We sum them together by lists, and then we solve it. And then in the results, the total cost is given by 66. But you can see the facility locations are slightly different than the P-center model. This one, you can see the covering area for the third facility is definitely much larger than the first one, the second one. So this is a slight difference comparing the result for P-center and P-median. For P-center problem, the coverage area for each facility is kind of similar, but for P-median problem, it may not. The total distance determines the results. So now let's focus on the fixed charge location problem. Similarly, we extend the median model. Our decision variable is still the location and then assignment. But here our objective is with 2 parts, right? One is the fixed cost part, and then one is the transportation cost part. So we have the same constraint, which is opening feasibility and then customer choices. Similarly, we can define the decision variable, and then we introduce the conversion ratio for the transportation cost alpha is 1. And then the problem structure, we can have 2 summations. One is fixed cost summation, and one is customer travel distance. And then we have two constraints, which we realize the same by summation of two lists, and then we can solve it very easily. So you can see the result. We have three facilities, 1, 2, 3. So this is kind of different from the P-media model, because here we further consider the fixed cost of a facility. In P-media model, we do not consider the fixed cost, we just consider the number of locations. So that means the fixed cost will affect the results. Although you can see some facility 3 covering only 4 points, and then facility 2 covered a lot of points. They are not very even, but then their total cost actually is smaller. And then finally, let's consider the capacity of the fixed charge model. So for the capacity, we only need to add additional constraint by k. We only need to consider one additional constraint, that is demand covered or assigned by facility J has to be small or equal to the capacity K. So here we just arbitrarily assume a value K equals to 5 for every candidate facility location. And then we can extend the problem by adding one constraint in the end and then solve the problem. And here you can see, because we set the capacity is 5, so there's 5, 5, 5, 5, 5. This is 4. Okay, we have 1, 2, 3, 4, 5, 6. Because the capacity limitation, we need more facilities to cover the service area. And also, you may notice that the facility may not locate at the center of the covering area, because this can better allocate the demand with the given capacity. So finally, we also introduced how we can integrate the package CVXPY and together with some commercial solvers. For example, here we use Groovy solvers. To install the Groovy solver, you need to type in these command lines, and then currently Groovy has supported the Colab with relatively smaller problem instances. If you really want to solve large problems scale, you need to install a Groovy license on your own computer, and then do not run Colab, but you can use like local Python files to run all these packages. Yeah, so here we have the same structure as before, which is the same as the initialization of the problem. And then we also have the same problem structure. Here we consider the p-center models with, we have 3 centers. And then in addition to original problem solvers, we can set the problem solver, which is cp.groovy, and then we just revise one line, and then we can use the Groovy package. So you can see when you use Groovy, it will have the Groovy log. Here it tells you that this is for educational license for non-production use only. And then this is a very small license, can guarantee you to run very simple toy examples. To really solve large-scale problems, you need to install your own licenses. And then it has some initial analysis on the problem, and then it can generate a lot of cut based on some advanced searching techniques. And finally, Groovy will give you the best objectives and then the best bound, and then here the gap is 0. That means it finds the optimum solution. And here the optimum value for our solution is given by 4.2, which is almost the same, which is the same as before. And then the solution here can be given